It's a pleasure to be here. Today, what I'm going to discuss is just an overview on looking at resource recovery from fecal sludge. And the perspective that I'd like to share with you is how to go about doing this. If we now trying to deconstruct fecal sludge or any other stream like this from an elemental basis. And basically, when I say an elemental basis, it is carbon, nitrogen, and phosphorus for the most part. And so, what is our objective here? We would like to go from something that looks like this, which could be sewage, which could be fecal sludge, which could be wastewater, to something which looks like this. And essentially, from a technology perspective, what the approaches which are followed is we basically put a box in the middle, which enables us to go from so-called waste streams to so-called clean streams. And so, in terms of biological treatment, let's say, of fecal sludge, of wastewater, of municipal solid waste, and other waste streams, what is commonly done? Maybe we can start there, and then perhaps we can build from there in terms of looking at this in a fairly more discrete and specific fashion. So if you look at the biological treatment of sewage at least, essentially what is done is that the first step is the separation of perhaps more degradable components, more biodegradable components, from the less biodegradable components, the more recalcitrant, more inert components. And this is primarily done by physical or mechanical means, just to separate out the solids, particulates, and the recalcitrants. And then what results is something which is a bit more biologically available, biologically degradable. And this is where I think some of the improvements could be proposed and implemented as well. So let's take a look at what exactly is done here. Again, just to recall, when I say elemental approach for fecal sludge, it basically refers to the primary constituents. And from a broad perspective, it's carbon, nitrogen, and phosphorus. And just to again remind all of us, in what form is carbon present in fecal sludge or sewage or most of these streams? In terms of an oxidation state, for most of these streams, carbon is present in the oxidation state 0. If you just take an elemental analysis and you take an average, carbon comes in at an oxidation state of 0. Today, what do we do to the carbon that comes in at an oxidation state of 0? In most contexts, in most systems, what we are doing is that we are putting in energy, we are putting in resources, and we are putting in money to essentially oxidize the carbon from C0 to C+4, which is carbon dioxide. And I don't think we need to worry too much in terms of the carbon dioxide footprint of these systems, because that's not the primary concern. The primary concern is the energy, resource, and money that we put in to the C0 carbon to take it to C+4, the CO2 gas. That's what we are doing. And in some systems, we also need to remove nitrogen, for instance, where let's say nutrients become a challenge. Again, what form is the nitrogen coming in with fecal sludge, with wastewater for the most part? Comes in as ammonia or organic nitrogen, again in the oxidation state -3, which is reduced nitrogen. And what are we doing? We are putting in money, resources, and energy to take this reduced nitrogen and oxidize it to dinitrogen gas. Now, dinitrogen gas is harmless. It's about 80% of the Earth's atmosphere. So, especially if you look at carbon and nitrogen, the theme is very clear. We are putting in a lot of energy, resources, money to oxidize these two elements, to carbon dioxide or dinitrogen gas. The phosphorus, fortunately, we do not redox cycle the phosphorus. And this is what we are doing. And, okay, so this is getting into a lot of specifics here. Let's take a few steps back and let's understand what this really means in terms of the energy footprint, let's say, of a nation. If we take the United States, for example, biological wastewater treatment, not of fecal sludge, but of sewage streams, constitutes about 6 to 8% of the national energy footprint. That's it's not very less, but it's not trivial either. But the important thing to recognize is that this particular process, where we have put in all the energy, money, and resources to oxidize the carbon and oxidize the nitrogen, this takes up 60 to 70% of a centralized wastewater treatment plant's energy footprint. So of that 6 to 8% in terms of the national energy footprint, the majority goes into this reactor where we are primarily oxidizing the carbon, oxidizing the nitrogen. And this is something where we can make a significant improvement, and that's what I will lead you through today. And so that was for just the overall process. We can quickly go through nitrogen removal, even though I won't focus on it for the specific details here. So how do we remove nitrogen from sewage, from wastewaters, and also potentially from fecal sludge? Again, nitrogen is coming in at this oxidation state of -3 amino acids. These are amino acids in proteins. That's where the -3 comes from. To remove nitrogen from the aqueous phase, what we do is we employ biological processes where we have to put in a lot of energy and we oxidize ammonia to nitrite and nitrate. Conversion to nitrate is not removal because nitrate is still fairly soluble, even more so than ammonia, and it is also somewhat toxic. Removal of nitrogen is by virtue of converting the nitrate to dinitrogen gas. And nitrogen gas is fairly insoluble in water and gets stripped out. That is removal. But in doing so, in engineering the nitrogen cycle, we have put in a lot of energy and we have put in a lot of money, and we are producing nitrogen gas. And if you look at the futility of this, well, maybe I should explain the futility of this. How have we got the ammonia? We have primarily obtained the ammonia by the Haber-Bosch process, which is still, I mean, we've done this for hundreds of years, maybe slightly more than 100 years, still very energy intensive, still primarily energy. So we've gone from dinitrogen gas to ammonia, we've used it, and then we've again put in a lot of energy and hoping that we can go back to nitrogen gas. And for the most part, we do go back to nitrogen gas. But look at what we have done. We've started at dinitrogen, energy, and we are possibly heading back at the same point. And whereas, if we say that, let me not redox cycle the nitrogen, let me just take the nitrogen as it is, coming into these waste streams, then perhaps we can reuse it for other endpoints, like agriculture, for instance. And so these are some of the links that we need to recognize. I won't talk about fixation. Biological phosphorus removal, again, when we engineer these reactors, essentially what we do is we subject the bacteria to cyclic anaerobic and aerobic conditions. I will not go through the pathways of phosphorus removal, that's not the point of this presentation. But the point is, we are employing fairly complicated and complex processes which are energy intensive, and all because we are relentlessly running after clean water, and that seems to be the only objective. We are not connecting the dots, we are not making any other links, and when we try to solve one problem, and this is something that I think Basican also mentioned yesterday, when we try to solve one problem in isolation, especially when these are local problems, we end up making mistakes. And so some of the mistakes that we are making here is literally in terms of the energy footprint, the cost footprint, and the resource footprint. And when we try and import this into places where there is no energy, or where there is little energy, then things don't run, things are not feasible. And so this is something that we can improve. Let's go back to some numbers that perhaps some of us that we can relate to at least. And so I will take the example of New York City because I think well it makes there's some context here, of course. In terms of New York City, at least, I think there are about 8 million people that reside in the 5 boroughs of New York. When the weather is dry, we treat about 1.2 billion gallons of wastewater per day. This is about 5 billion liters of wastewater per day. What is this wastewater carrying? It is carrying about 1,800 tons of organic carbon coming in at the oxidation state of 0, and we are primarily trying to oxidize it to carbon dioxide. This wastewater contains nearly 300 tons of nitrogen in the oxidation state of -3, and we are putting in energy to oxidize it. It contains 60 tons of phosphorus per day, and we are just dumping it because New York City does not have phosphorus limits. And this is what we are doing. Now if we can just look at this system and try and see, well, instead of looking at this as a problem, is this really an opportunity here? Can't we just reorient our thinking, our technologies, which are already there, and we don't have to go too fancy here, and I'll give you some examples. Can't we look at this as an opportunity and perhaps recover some of the 1,800 tons of organic carbon, some of the nitrogen, some of the phosphorus? And this is just in the city of New York, on a dry day. Well, you all know, I think we are having a slight shower problem in New York City today, for those of you who've been looking at the news. I think things are almost coming back. Anyway, so that's the opportunity. How do we do this now? Again, talking in terms of carbon, nitrogen, and phosphorus. So I think the first statement that I'd like to make is, instead of oxidizing the carbon to CO2 and putting in all these resources, perhaps we can look to reduce the carbon, C0 to C-4. What happens when we reduce the carbon to C-4? Well, we get methane. And frankly, if you ask me, there's really not much novelty in anaerobic digestion today. We've been doing this for, again, hundreds of years. And again, I'm sorry if this offends some of the audience here. I think methane is one of the most boring endpoints that we can handle. But there's also a challenge with methane, you know. Anaerobic digestion does not produce pure methane. It produces a mixture of methane, carbon dioxide, and moisture. And this is it's not trivial to use just anaerobic digested gas for many objectives. We need to clean it up if we want to go to some chemicals. And there are options, and I'll discuss this as well. On the other hand, the reduction of C0 to C-4 is still fairly rapid. And then if we can turn the aerobic processes to anaerobic processes, we can get for sure methane. But in between C0 and C-4 lies this vast space of 4 electrons. 4 electrons is just fascinating because it completely opens up the carbon landscape to many, many, many different chemicals where we can get just commodity chemicals, fuels, and energy as well. And then it's not a question of this or that. We can still get the methane. We can still get the methane. Okay, so once we've taken out the carbon and actually recovered some of this, what do we have left? We have phosphorus and nitrogen. And during anaerobic conversion processes, it's quite beautiful in a sense because the phosphorus also precipitates out with the cations which are added. So what have we done now? We've recovered the carbon in a form which is more useful than carbon dioxide. We've recovered the phosphorus, and then we are left with nitrogen, again in the oxidation state -3, because under anaerobic conditions, for the most part, nitrogen is not redox cycle. So then we have 2 options. We either recover the nitrogen or remove the nitrogen. If you want to recover the nitrogen, I think today most of the technologies, feasible technologies, are are both biological and physical chemical. If you want to just remove the nitrogen, I think we should still go for biological systems. So this is not a random order. What I propose here is a specific hierarchy of steps, or rather sequence of steps, whereby we address specifically in a targeted fashion carbon, phosphorus next, and then nitrogen, and primarily oriented on anaerobic processes and also primarily oriented towards recovery. And a lot of this, we don't have to invent new processes. We don't have, this is not Star Trek. This is something that we know how to do. It is just reorienting the processes to an endpoint. And the endpoint becomes very important because sometimes we don't want to be recovering chemicals in a place where there is no use for chemicals. Perhaps we can go to methane and perhaps some more interesting endpoints, more interesting than methane as well. Monetizing these chemicals, of course, that adds another layer to all of this, and that could also guide our decision. And so, when we talk about engineered resource recovery from waste streams like fecal sludge, what are we talking about? At the very least, we are talking about energy. We are also talking about commodity chemicals, and this is something that we should not forget. And there are several spots along this process chain, if you will, where we can recover both chemicals and energy. There's just energy here, and then also chemicals and energy from the different liquid and solid streams. And you know what happens with all of this? I think I've stopped using the word sanitation or wastewater. We've been focused on recovering products, right? Water becomes the bonus. Human health, environmental health becomes the bonus. This is where ideally we'd like to be. So we're not going in and putting in all the resources to solve one problem. If you change the focus to recovery, sanitation becomes the bonus. It could become the bonus. And so what are some examples of these chemicals? I'll tell you what we do as a group, not in the lab alone, but also all across the US, but also in more and more parts of the world. We convert organic chemicals to alcohols, not potable alcohols and acids. We also convert them to precursors of synthetic soils, which is somewhat attractive, chemicals, fertilizers, of course. And then maybe I can spend some time talking about the project in Kumasi, Ghana, which is directly funded by the Bill and Melinda Gates Foundation. Here, the focus is one specific product. Primarily, it is biodiesel. And then this is the schematic of the biodiesel production process. Essentially, it involves anaerobic conversion of carbon to methane, of course, but also to a lot of other precursors which we can tap and feed into the biodiesel synthesis process. I won't go into too much detail because of time constraints, but if there are questions, I'll be happy to answer them to any degree of detail. The data is just not here. And so, well, Kumasi is about an hour flight away from Accra. We've chosen to put our pilot process in a landfill site, so we don't have any problem to get the fecal sludge. In fact, the design capacity is 1 truck of fecal sludge per day, which is 10 cubic meters per day. We are entirely surrounded by fecal sludge lagoons and a landfill. And we are completely off-grid. There is no power, there is no clean water, there's no gas available. And so this is really the heart of the system. It looks a lot more complete now, but the reason I wanted to show you this is because if you look at the design, it's basically a very conventional anaerobic fermentation digestion process. What we are doing is we have allowed ourselves the flexibility to tap into this process at multiple reactors down the chain. The last couple of reactors will of course produce methane, but we have the flexibility to tap into the chemicals which are precursors of methane, which are also precursors of biodiesel, by the way. And so the project, the construction is complete, and we are just about getting ready to start accepting fecal sludge to put into the process. We started with that simplified black and white diagram, but as we went forward, we've somewhat realized that the procedure is a bit more complex, and we are working through this now. In terms of what the process is designed to do, the design capacity is 10 cubic meters per day, and there are 2 real sources of biodiesel. We can directly tap into the lipids which are present in fecal sludge, and when we started this project, we really did not know what fecal sludge in Kumasi looked like or in Accra looked like. We've heard a lot about how fecal sludge is very site-specific, and we were not only going after carbon, nitrogen, phosphorus, we also wanted to zero in on the lipid fraction, which is what we can use to make biodiesel, free fatty acids, lipids, and so on. So we now know that there's about 50 kilograms per day coming in, which translates into about 57 liters per day of biodiesel. Again, which is not trivial. At least we can use it to fuel some trucks. But this is not the only thing that we will recover. We will of course go to methane, and the nitrogen and phosphorus can also be recovered as well. And this is just to show you what we've been doing. We've been drawing fecal sludge and making biodiesel out of this. Now essentially what we are doing is we are doing on-site testing, lab testing in Ghana for the most part, trying to fill in all the gaps that we need to make the pilot successful. And then there are other opportunities as well, and perhaps I can take a couple of minutes to address this. So there are 50 liters of lipids coming in, which we can convert to biodiesel. But look at the rest of the carbon which is coming in, C0. We have developed a process that we can use to take that carbon, and any organic carbon for that matter. We ferment it, and we convert the fermentation products into biodiesel. So this opens up the biodiesel production train quite significantly. We don't have to rely just on lipid-containing streams. We can basically go to any organic stream, ferment it, produce lipids, and go to biodiesel. And this really can then make this process fit into not only fecal sludge, but this opens it up into municipal solid waste, brewery waste, which is rich in organics but not lipids, and so on. And then just one more option for process improvements. What do we do with the methane? I mean, I've been giving methane a very bad name, but maybe now I can tell you what we can actually do with methane. And this is very site-specific. It's very endpoint specific. You know, in biodiesel, one of the principal chemicals that we need is methanol, to make the fatty acid methyl esters. And then we have methane. What we have developed is a process that uses nitrogen oxidizing bacteria to oxidize the nitrogen, but also oxidize the methane into methanol. Now you must all be thinking, what is this guy talking about here? I mean, I'm just producing methane, I can make cooking gas, right? Where is the ammonia coming from? Where is the methanol coming from? But I can answer this, right? The carbon is going to methane, and the methane of course can be used. Where is the nitrogen? Like I said, in digestion, just the carbon is redox cycled, it's reduced. The nitrogen and phosphorus are not redox cycled. The nitrogen is just coming straight out. So now what we are doing is that we are taking the nitrogen and oxidizing the nitrogen and using that to oxidize the methane to methanol. What do I do with the methanol? Produce biodiesel. So we are closing some of the loops here in terms of the overall process efficiency, in terms of the overall process yield, in terms of the overall process kinetics. And finally, what I'd like to close with is by saying that, sure, resource recovery is great, but we need to be very cognizant of what the endpoints are. I don't want to make methanol in a place where it cannot be used. But I can tell you a lot of applications for methanol, perhaps not today. But again, we need to be quite savvy in terms of how we employ resource recovery. So I've divided the world into 3 broad categories. the developed countries, the underdeveloped countries, and the developing countries. Let's start with the developed countries and ask two questions. What typifies these countries, and what do we need to recover in terms of resources? So in terms of characteristics that we can ascribe to developed economies, there is food security. There is very good technology and engineering in terms of the backbone. What do we do with carbon, nitrogen, phosphorus? The answer with phosphorus is always the same. We recover the phosphorus, no two ways about it. What do we do with the nitrogen in a developed economy? Do we really need to recover the nitrogen? Perhaps not, because there is existing food security. Finally, I think I went through this a bit quickly, but the carbon recovery technologies, unless you go to methane, are a bit involved. And so they will only succeed if there's good technological backbone. But in a developed economy, this is there. So for this sector, let's recover the phosphorus, recover the carbon, perhaps not look at the nitrogen for recovery so far. Let's go to the end of the spectrum now. There are big questions on food security. Technology, engineering, and education is really not the strongest asset. What do we do with carbon, nitrogen, phosphorus? We know the answer to phosphorus. Let's recover the nitrogen here because it can go towards improving food security. Do we really need to recover the energy when there is no food? Perhaps not. Let's put food on the table. Let's go to the most exciting, the economies in transition. There are some questions on food security, not as good, not as bad. The technology and engineering, on the other hand, is quite remarkable. I mean, I'm thinking specifically of Brazil, Russia, India, China, and South Africa. So very good engineering know-how. We know what to do with phosphorus. If we recover the nitrogen, we can improve food security. But here, let's go ahead and recover the carbon as well, because we have the resources, because we have the human capital to do so. So I hope at the end, I've given you just a little bit in terms of food for thought. The elemental approach not only tells us what technologies to put in, what the endpoints can be, but it also gives us a framework of where to recover what. That's all I have. Thank you.